Hello, ladies and gentlemen. Hello to a new and great tutorial and movie and also lesson in the same time about EEPROMs. And more specifically, this EEPROM that I have already. I bought it 3 years ago, I believe. Let me check. Yeah, in 2022, and now is 2025. This is the chip here. This is its datasheet. The name of the chip is ATMEL 24C32 is what you have to retain to remember. This file here is the price that I paid. Actually, that period from 2020 and 22 was quite on the top, on the verge of high prices everywhere, especially for chips because of COVID hysteria. But I did pay this sum that you are seeing here, including the transport, the final sum of money that I paid, not for 10 pieces, but for 20 pieces. So it's 2 times 10 pieces. In total, I have 20 pieces of this little EEPROM, which is a serial EEPROM. Why I bought this EEPROM is because, yeah, you see, this one, I bought it, ATMEL 28C64, and this is actually a parallel. So it says here in the name, parallel EEPROM, and it's very easy, very comfortable to write data inside it and then to read from it, because it's parallel interfacing. So I always praised and I always mentioned, and I'm always sticking with this idea of using parallel chips in general. Doesn't matter what they are, but in this case, they are these EEPROMs because of the ease of using them, of accessing them, of reading and writing to them. It's very, very easy, very user-friendly, and very intuitive to work with them. I mean, you still have to learn them a little bit, how to actually program them and read from them. You have to build a little bit of experience, but it's very, very easy to work with them. But in the same time, when I bought this on October 8th, here on the same day, I bought this serial EEPROM 2432 because I was curious about it, how hard it can be. I actually tried to read and write to this serial EEPROM using the PIC microcontroller. And if I remember right, I also stay with a friend from England. He's an old guy, way older than me. We could not do anything. I mean, I pushed it as hard as I could, and I couldn't break it. I couldn't understand it, how to write to it. And with the help of that guy, both of us, we couldn't figure it out, how to make it work, how to write and then to read from it. We didn't figure out the protocol from only reading the datasheet. That's what I'm saying. The datasheet is not that user-friendly and is not that complete, I may say. It should have some sort of example code, both in assembler and in Arduino code, in these two languages, in lower level and in higher level. So that's why I'm saying they are quite incomplete. They are like, here's some data, but they are like little crumbs. If you are smart enough to use these crumbs and understand how to program it and to read from it, then there you go. If you are not, then you are stupid. That's what the datasheet is telling you, in other words. But recently, with the help of ChatGPT, I also made a test program in Arduino, and I also managed to understand why this chip was a bit more harder to understand and to deal with by only reading from the datasheet, like I did myself alone and later with my friend from England. I made this page, a Q12 page. This is my brand, Q12, and I'm an artist. That's why I'm saying illustrations, because I'm an artist. Let me start with the beginning, actually. This is the pinout of the chip, my chip that I'm having. Here is on AliExpress. These are the current prices for them. I wanted to make a comparison between the prices I paid in 2022 and now in 2025. So I paid this sum, 2.87, for 20 pieces, not for 10. And let me actually search here if I'm lucky, 20%. Yeah, check this out. This price is without the transport. Let's check the transport. It looks like it's way cheaper now than before, but oh, free shipping. Very cool, very cool. Oh, check this out. This is SMD and this is DIP8, which is a bit more expensive. Yeah, but still way more cheaper than the price I paid last time. But I wanted to show you how they are looking and what chip I'm having and I'm working with. I'm having it here from the top view. I edited everything here. So I have this picture here that I edited, and I also included here in my Q12 page. So this is the chip that I'm having, this DIP8 chip. This is SMD one, and this is even smaller SMD than this one. Okay, so this is the image that I model it here, and I also copied this pin configuration. The pinout of it is quite simplistic. It doesn't have too many pins on it. After I figured out what these pins are used for, this is what I will discuss and explain in this little tutorial about this chip, this specific one, because this is the one that I'm having. That's why I'm talking about it. So A0, A1, A2, it means the addresses, address 0, address 1, and address 2. And they are used, as is mentioned here, for I2C. It actually, in the original datasheet, doesn't actually mention that is for I2C, but I added this little detail, which is very important for it. Originally, when I first looked at the chip, I thought this is a way of programming the data of the chip inside. So I was a little bit confused by this little address. Actually, the address was the biggest problem I had. I didn't understood, and the other guy didn't understood either how to address this chip, because it was a little bit confusing, only reading from the datasheet and without the help from ChatGPT. ChatGPT really did help me. In a single day, I managed to do the entire work. The entire time I spent doing it manually by myself without any help, I spent like probably 1 week and then I give up. But I store this problem in my memory, in my human memory. I store it for later to resolve it. And after I play with ChatGPT lately, with some programs, with some discussions, it popped out that all the problem I had, and I tried, and I was very, very reticent. I didn't really wanted to try it with ChatGPT. I was 50-50 sure if I will resolve it. I was thinking ChatGPT will throw some garbage information, but it really, really helped me, and it really cleared up some details that I was absolutely unaware of. By the way, this is the first time, with this occasion, I have to mention this very important detail, that this is my first serial EEPROM that I'm using, that I'm trying to drive in my life. This is the first one in my life. I never did it before. So this presentation, this is about it. My first success is better say, and my first successful driving and successful writing and reading from this chip, actually using it. As a test, I'm quite pleased and I'm quite happy that I managed to figure it out and to finally make it work. Because I don't really like to have components in my arsenal of components of chips that I don't know how to use them. I don't like this. So I want to be able to use everything I'm having in my arsenal. And this was a kind of a challenge. That's why I bought it, as a challenge to poke in it, to try to figure it out without external help, because I don't have that external help from no one. It's not that I don't want it, it's because I don't have it. It's impossible for me to talk with specialized or professional people. So I'm the average Joe. I don't know everything. I have a limited knowledge bank. Okay, let's get back to it. So let's get to the pinout, because that's what I was talking about. So the addresses of the chip are not the addresses of the internal memory as I originally believed, and I was thrown off. I was very confused about it. And then with the ChatGPT help, I figured out that these are actually the communication pins for the I2C protocol. Pretty much what this is doing, you can daisy chain, you can put in parallel multiple chips, not that many, actually only 8, maximum of 8 chips with these address combinations that you are having here on the same 2 wires from I2C, and that's what they are for, these addresses. And then the other pins are the power pins. This is plus 5 volts VCC, and this is 0 volts, which is ground. This is write protect. You can see it here, write protect. We will get to it later. And this is the actual I2C communication. Serial clock and serial data is cycle and SUDA. This communication is both for writing data into the chip and reading from the chip by a microcontroller. So this kind of component, this EEPROM, is working hand in hand with a microcontroller or your computer. But a computer is too expensive to use. So microcontroller is way more cheaper and mostly used all the time, especially for serial EEPROM. The parallel EEPROM, you don't need a microcomputer or microcontroller to talk with this chip. You can actually do it with wires. And I did this experiment and I did this demonstration in an earlier video some time ago. But this is a bit more challenging, and you really have to use a microcontroller or microcomputer if you want, especially for this serial EEPROM. You cannot drive it without. They are literally shaking hands. They are holding hands together, one with the other, but not without the other by itself. That's another very important detail that I wasn't sure about it. I was thinking maybe I can drive this, especially this serial EEPROM, without a microcontroller by itself and from some logic chips, gates, XOR gates, AND gates, like that. I was imagining before knowing everything I know right now. So that was my expectation, and that was my vision, that was my idea how to use it. And no, you cannot use it without microcontroller. It's impossible. Trust me on this, it is impossible. You will see why in a second, because it will be clear how complicated it is to drive it, and that's why you need a microcontroller for, or a computer if you are if you don't know what to do with your money. All right, so this is the pinout. This is what they mean. Here is the datasheet that I have it for it. The 32, it means the memory inside, how much memory is having, and the 64 is bigger and better than the 32, but the address, the structure inside it is the same for both of them. And now, in retrospect, I don't know why I didn't choose 64 to have a better and bigger memory, and why I choose 32. Probably because of the price. Maybe I checked the price back then, and it was maybe too expensive for the 64, and I chose 32 because I find it more cheaply. I don't know. But usually they are around the same price with very little difference in pricing. I should have chose 64 now in retrospect. But well, from another point of view, I wanted to understand how to drive it. And I believe at that time when I bought it, before I bought it, I was thinking maybe if it's a smaller memory, maybe it's easier to drive. But it's having the same way of driving either way. Doesn't matter the size of it. All right. So I included this little pinout diagram here in my page, my Q12 page. You can see it here on the top. So this was the main problem that I had, how to actually drive it. So this is the title of my Q12 page that you are seeing it here. How the fuck should I drive it? Because I had a very big problem driving it. I didn't know how to drive it, and I didn't completely understood from the datasheet how to do it. And this is the title of it. And here are some data about it. 32 kilobits is, pay attention, that is in bits, not in bytes. This means, so this 32 kilobits, it means 40,000 bytes or 4 kilobytes, you see? So 32 kilobits or 4 kilobytes. and it's having this address range from 00 to 0FFF in hexadecimal. And now let's get into the memory structure, what is having inside it. I will directly reading and explaining directly from this page because I did put a lot of thought in it, and I did concentrate it to make it as easier to read and understand, especially from a first view. When you first look at it, you get it. I simplified it as best as I could. So this memory chip is having data inside it, is mentioned here, and also here with gray data bits. And this is a bit. This square, all these squares, these blue squares here are bits. They are representing physical bits, like little square. And it's having 8 bits. 1, 2, 3, 4, 5, 6, 7, 8, and they are arranged in addresses. One line of bits, it means address 0. The other line of bits, of 8 bits, it means address 1. The next other line of bits, it means address 2, and so on and so forth, until we are reaching the maximum, which is 40,096 bytes. The address is 40,000. Why bytes? Because 1 byte is 8 bits. You see? 8 bits. So this 40,095 bytes, it means this 32,000 bits. This 8 bits arrangement inside. So this graphic, what you are seeing until here, in this left side, all these bits, all this graphic represents only the data bits, the data that you want to store in it. The right side, this one, is another story. This is about the address, how the data bits are arranged inside the chip. And here, as you can observe, I'm having a designator, decimal. Here is in hexadecimal, and here is in binary, as you can see. This decimal, it means 0 to 4095. This hex thing, it means these numbers here. The binary is actually the binary form of the hex, but all these three rectangular blocks, decimal, hex, or binary, they are exactly the same thing. They are not separated things. They represent the same thing. This binary number with only 1, it represents address 1, or in hexadecimal 0001. And this last one, so this entire number of bits, it means in hexa this thing here, or in decimal if you want. You can actually test what these bits, if they correspond to these numbers. And let's try it actually. So I have 0000. So I'm reading this, and then for 111, 111, 1, 4 of 1, another 4 of 1s. Let's see, I copy it and paste it, and another one. So I'm having this exact number, and it should give me 0 FFF, 3 of Fs. And now let's convert it. It assumes you have a 0 in front of it. It's the same as putting a 0 there, 0 FFF. 0 is omitted in the front. And also the decimal 4095, as you can see here. That's what all these numbers, what they mean, is the same exact thing. And here, I'm explaining a little bit more better. You can see a green, slightly green tint block here. And here is a slightly bluish tint block. So I have 2 blocks for the same hexa block. So these are binary blocks, 1 and 2, but they represent that. It's actually 8 bits I'm mentioning here. This 8 bits, it represents 1 byte, and these other 8 bits, which are these ones, and they represent another byte, or byte 1 and byte 2. And together, they form 16 bits address, or a 2-byte address. So this is the address structure inside it, and I didn't know that is having it like this. I didn't pay attention, I was confused, I was thinking on something else maybe, but I didn't get it. I didn't understood it from its datasheet. Maybe it is specified there clear enough, but it wasn't clear for me, and I didn't get it. I actually made a mistake when I first made this page, this Q12 page. Let me check it, zip. I have a bad one. When I started, so this is how I imagined it in the very beginning. And I actually finished the entire page, but then I realized the second day I made a mistake. I confused the data bits with the address bits. So this is wrong. The wrong one is a bit more, maybe easier to visualize it, maybe like this, but it's not correct. So the data and the address are 2 very different things. They are the only constructive components. This chip is having only these 2 elements, the data bits and the address structure, and that's it. That's all there is to this chip. Is that simplified? Is that easy to visualize it in your mind? It's having 2 components, data bits and address structure. And after figuring out the address structure, I actually stay in talk with ChatGPT, and he mentioned a couple of times that the size of the address structure and the size of the data bits, these 2 blocks, this data bits and this address block, that you have to separate them in your mind. There are 2 distinctive blocks. The ChatGPT did specify multiple times actually about these 2 different blocks, how I'm calling them right now. He didn't call them like that. He was specifying them in a context. And I still made this mistake of putting together, because I didn't know how to visualize it. I had a very big problem of visualizing it. I'm very glad that I managed to correct myself and to make it clearer, and making it correct the second time. It doesn't matter how many times you are correcting something. All that matters is that you finally get to understand it to its core. So that's what I did here. I'm quite happy with this structure that I managed to illustrate. Let me tell you a little detail what my expectations were and how I was imagining, but it was nevertheless something that I never thought of. I didn't expect it to be this address structure at all. This is how I was actually imagining for a very long time actually. I was thinking, yes, it is having 8 bits of data internally. On addressing, I was thinking until here only this block that is having. I was thinking it's having only 8 bits of address. It never crossed my mind it is having more than 8 bits, that is having this 16 double bits. This is how I was imagining in the very beginning when I started with this chip, with this serial EEPROM. I was very sure it is only 8 bits address and the data structure inside it is complicated. I was sure the data structure, these data bits are very weird displaced or arranged. With time I realized, and with the help of ChatGPT, he did greatly help me understand this structure inside it. Without it, I could never thought that this was having two blocks of 8 bits, 16 bits in total. This was the shock when I realized that I was wrong all the time, and that this is a bit more than what I expected, 16 bits instead of 8. So that's the comparison, how it really is with how I was imagining it to be. And it's good to make this comparison and to remember them, because a lot of people are like me. They are making the same mistake, especially in the beginning, and especially without external help, especially if they are on their own without any other help, professional help or whatever. And they have to figure out all this by themselves. And we are humans and we are making stupid mistakes. We are champions on stupid mistakes. And I am one of that champion on presuming wrong information. So we all need correcting. So right now in this fragment, I'm explaining how to read this data. It's like a little about where 0x002, which means this address specifically, but it can be anything else, reads as memory address number 2, which is this one, is the same, absolutely the same thing. It's not something different or separated. That number reads as memory address number 2 in a 16-bit or 2 bytes of memory space. It means this form. This is the naked, the raw form of it in binary. Using hexadecimal is a way of helping, not dealing with all these 00 and 1s, because it's very confusing. This is helping you compress the data that you are seeing when you are reading a naked binary number like that, especially in 16 bits form like it is right now. It's a bit more complicated to keep track what is what, but it's still hard to deal with hexadecimal. You cannot do it in your head. You need a calculator like this, or a converter, or a hand calculator if you have those. I don't have. I have to rely on internet to help me about it. You still have to convert from one to other to visualize it, and also into decimal as well, to see exactly what address you are at in a specific moment. So let's get back to my about line here. And 4095 or 0xFFF, it means this address 4095 or 0xFFF, or this number. That's why I put this equals here. It means or, doesn't matter. All they are the same thing, and they represent address number. They represent this block here of address, and not the content or the data. You remember I split this in 2 blocks. This is the data block and this is the address block, because this was the biggest confusion I was making, and that's why I'm making this movie about, to be extraordinarily clear, to be very, very easy to say it. I am jumping directly into the code. I will show you the code a little bit. This is the code that ChatGPT make it for me. This is the entire code from here to here. Doesn't have a loop. It's only having a setup, and that's it. So in the setup is having all this mambo jumbo, and I'm also using outside function that is used inside here. ChatGPT gave me these 2 lines, and they were here and also here. So I simplified it with one single line. Because why I simplify it like that? Because I wanted to write the binary number like you are seeing it here, 16 bits in binary. In this example, it represents address number 2 or the hexa 0x2. This function that I'm having is containing these 2 lines, very important lines. I copied what ChatGPT told me it means and what it's doing. This code splits 16-bit value, which means this address structure, this 2 bytes, this is 1 byte and this is the second byte. Yeah, you can see it here, 1 byte and 2 second byte. This code splits the 16-bit value into 2 separate 8-bit value, so they can be sent 1 byte at a time over the I2C. Why? Because I2C sends 8 bits at a time, but the EEPROM's memory address is 16 bits. So we manually split the 16-bit address. So all this little function, it is literally splitting 1 byte and send it over the I2C, and then it's another byte, and it's sending this to A2C. 1 byte at a time, not the entire 16 bits or 2 bytes at once. So you have to do it programmatically. And this is a trick that I couldn't figure it out by myself ever. Forever. No fucking way I could figure it out by myself. So this is a special way, a special directive, a special way of dealing with this type of memory, and I couldn't make it by myself. And with my other friend, we had no clue, no idea how to deal with this. And that's it with the code. This is it. It's that simple. It's very, very simple, and it's working. That's the most important thing. It is fucking working. Here I have a comparison table because I was curious. I actually asked ChatGPT if there are other weird address structures like this in other serial EEPROM. Like I'm having here 16 bits or 2 bytes. Like I'm having here this byte 1 and byte 2. Maybe there are other structures that are splitting in many bytes, like byte. Right now I'm having here byte 1, byte 2, and next byte 3, byte 4, byte 5, and etc. Maybe there are more weird shit like this that I never thought of it. And ChatGPT told me, no, it's not really like that. All these chips, they are all stopping at 2 byte address. And if you need more than 2 byte address, I actually write it here. This is the subject about it. So let me read it and you will get it, how it is dealing with even greater space. I actually have this picture by itself. So I cataloged a couple of chips, as you can clearly see. It says here my chip, this is 2432, that's why I told you to remember this name in the beginning of the movie, because I'm referencing it in the context of other chips, what this chip is having compared with other cousins. So the memory is 4096, and you can see here, this one 64 that I mentioned, I should have bought this one, which is having double the memory than what I'm having here, but I bought this to learn. This is my lesson into serial EEPROMs, not parallel. And here is a very interesting column. It says blocked, but blocked not by blocking something, by opposing something, blocked as a block, like this entire rectangle is a single block or a single module. So the correct term is blocked and not module for some reason. So this is very important. If it's blocked, it's more harder in code to deal with it. If it's not blocked, like it's mine, so my chip is not blocked, it's easier to deal in code with it. And then address pins usable. Again, these are the I2C address, and these are the maximum chip, or in my case, how many 24C32 chips I can put on a single I2C bus in parallel with each other to have a bigger memory pretty much. And I can use these address pins to create 8 addresses to communicate with different chips on the same I2C bus. So imagine this is the address of the street and the chip is the house. I can put on my street, I can put exactly 8 houses, no more. I can put less, but no more than 8. This is the maximum because it's the maximum you can combine all these addresses between them. It's dependent. This 8 is actually 111. So this side of this thing is about the number of chips and addresses for the I2C, how many you can put on the same I2C lines. While this part here is some internal specification. This is how you talk with the chip here. This is what the chip is containing inside him internally. This is external and this is internal pretty much, okay? And this blocking is very, very important. Let's read about it, what really it means. So this is the same picture that I just showed you. When an EEPROM like the AT2404, this is not my chip. This is just an example chip here. 04 is, where are you? Here. This is an example. So this chip uses bits of the I2C address to select memory blocks. Yeah, you see the block that is having. It uses up the address space, which limits how many separate chips you can connect on the same I2C bus. As you can see, only 2 maximum chips on the bus. Remember, this is external and this is internal. So in the external, you can connect 2 chips on the same I2C bus, okay? So what this is telling you that you can use only one single address pin from this chip. You can make it either 0 or only one single address pin. Why? Because the other 2, A0 and A1, are used to create these blocks. So they are using the pins of the external setup. So the same pins that are used to link multiple chips one by one, they are using the same pins to switch the internal blocks inside to get more memory. That's what they are doing here. The term blocked or page or banked in the context of 24C04, 08 or 16, so 04, 8, 16, all these 3 guys, you see here, they are all blocked. Refers to a memory division technique where the EEPROM's memory is split into sections or blocks, like I said, and those sections are accessed using bits in the I2C device address, not the internal memory address. So you cannot access the blocks from code, you access the blocks from the external pins of the chip. You hardwire them specifically to access certain blocks. Or I believe you can access them from code as well, but you will use more wires. Instead of only I2C wires, you will need more wires from your microcontroller to the chip itself to switch between these blocks. The problem, limited addressing range. So this is a very good example. 1 byte it means 8 bits, okay? Can only address 256 bytes, or from 00 to 0xFF. This is not my chip again, this is just an example, and is this one here, has 512. So it's double from what you can actually access in code, which is more than what 8 bits can access. So how do you access the extra memory? You split the memory into blocks and use bits in the I2C address to select which block you're talking to. I hope it's clear enough. This was an entire novelty for me. I didn't fucking know about it. This is the first time when I'm hitting this wall, this very strange and very particular and very interesting way of doing things. For me, how I'm seeing it from afar is that they literally experimented with these EEPROMs. They didn't like them. They made a lot of mistakes. I believe these are mistakes. This is how I'm perceiving them. This blocking shit, this is bullshit. This is just pure experimentation. In reality, I don't think they are using these ones with the blocks in the industry or in, I don't know, in police, in army, in medicine, all the boards that are made. I don't think they are using this type of chips. I believe they are making them commercial only because this single reason they are fucked up. In those fields, more important fields, they are using more simpler and more easier way to address them and to work with them. I got extremely lucky. I got extremely lucky from this point of view of blocking. I didn't have absolutely any clue when I bought my chip. I got extremely lucky to buy it without having this issue of blocks inside it. So it's very easy to access, relatively easy to access compared with other chips. And fucking hell, I kind of dodged a bullet here because I didn't know better. I had absolutely no idea. I am very lucky to actually use all these 3 pins of the chip and create 8 different addresses for 8 chips to put them on the line and use them in parallel pretty much. And with bigger memory to increase the memory pretty much. That's why you need to put them on the I2C line. Yeah, very lucky I was. I am considering this one as well to buy it in the future, maybe. Why? Because this one is actually using, you see here in this example here, it can only address 256, and I had this discussion with ChatGPT. My chip, what I'm having is 512 bytes, so it must have this weird address structure inside it to send 8 bits at a time to the I2C bus. But that chip, as limited as it is having only 1 single byte, only 8 bits of address, and only 8 bits of data. And it's exactly how I imagined it in the very beginning when I know nothing about these problems and these complications that you are saying here. This was another discussion with ChatGPT, and he did confirm to me that indeed this is the step down, non-complicated chip from my chip that I'm having right now, but a bit more simpler to code, to address. The downside of it is very low in memory, extremely low in memory compared with what I'm having. And there are even bigger memory chips than this, also without using blocks. I did ask the question what these other chips are using. If they are not using the block system, what they are using to, you can use the same 8 chips on the same bus, but with extremely bigger memory address, how they are switching everything. And also keeping the same structure of 2 bytes, like here. So for this example, addressing structure, yes, the same 2-byte format, exactly like I'm showing here, this 1 and 2 bytes. So pretty much the difference from a bigger chips, these bigger chips from my chip, what I'm having here, this 32, these are using the entire address bit. If you can see here, you see the address is up to 4095, but it's 0FFFF. So those other chips are using FFFF, the largest one, not this 64, but probably this 256 is probably using that FFFF. So this is my question. What's the 0xFFFF 4Fs here? Decimal is pretty much to convert this hexa into decimal, and the maximum is 65,535. This means 65 kilobytes. This means is double than this, so it means AT24C32 is the actual maximum address that you can write in code using all these FFFs. So that's the difference from my chip, how many addresses you can write in the hexa. For my chip, remember my chip was having 0 and 3 Fs, 0FFF, but the maximum is actually not specified here, is even larger than this, is 500, is somewhere here, is 512, and is 65 kilobytes large to actually use this entire addressing for Fs. So for this lower 32, 16, and this 8000 bytes, you are using less numbers in this address. So that's the difference without using the blocking. This is one reason why I think these are just very weird experiments using the blocking system, literally cutting the maximum chips on the bus and getting into the pinout from the I2C and use it for completely other purpose. It's not correct, it's not right. It is doable, but it is very experimental in my book. I think they experimented, they didn't like it. Many people, most probably like me, this is my first impression. This is my first time when I'm seeing this shit with blocks. And many people like me, they were like, get the fuck out of here. And they didn't use them, most probably, is my impression, is my guess. And they sell it to the general public that they are happy if they have such EEPROM in their arsenal, and they will deal with these problems, these weird, shitty problems. That other chips, they don't really have these problems to address. Again, this is my impression, this is my very subjective impression, this is how I'm seeing it. Somebody else can come and shit on my head and tell me that I'm stupid for X reasons. But this is my first view on them. Again, this is my first time dealing with this serial EEPROM chips. And that's why I specified here, this is dealing with the internal address of the chip, the structure. That's why I said here on the top is address number 1. And here on the bottom, I have the second address of the chip, of the same chip, that is external, that is using the pins of the chip. They are used for I2C communication to link these chips in parallel on the same 2-wire bus. It's quite a universal table. You can find this table, and you can use this table for any chips that are using I2C, and they are having only 3 pins. And usually they kind of having only 3 pins. It's like a untold rule. So 8 is good enough. It's like that, you know. So this is universal for, not for these EEPROMs, but for any other chips that are using the I2C addressing, including this EEPROM that I'm having. And these are the lines of codes and what they mean. So this is the actual address of this chip 0x50, it means AT24C32, this is my chip, base I2C address when A0, A1 and A2, so A0 to A2 address pins are linked, all three are linked to ground, and they give you in code, they give you this number. Actually, you can see these bits specified here, these last 3 bits, you see them here. These are the only bits are changed. You see one here, and you see only one here, here, and they represent these addresses. This is the base address. When you put all these external pins of the chip, you link them to 0 volts, and they represent 0 logic, like you're seeing here. And here is actually 5 volts, represents a logic 1, and represents this address. So this is hard-coded externally to change the address of the chip. And you also have to specify it in code as well. If you are using this second address, you have to also specify it in code as 51 there. Why? I don't know. It should be automatically detected, but it doesn't. It's like more like a confirmation here that, yeah, expect to be like that. So this 0x50 in binary means this number here. And it means that I2C address for the EEPROM, if A0, A1, and A2 are all tied to ground, while request from EEPROM address 1, request 1, this one byte from device at the address, at this address. This allows you to connect up to 8 EEPROM chips on the same I2C bus, each with its own address, using just 2 Arduino pins, serial data and serial clock. I did had a problem with this little thing. How do you change the address that you are reading from? Because in this form, you are specifying here the address of the I2C bus, but not the internal memory address of the chip, and you are requesting 1 byte to read from it. But it turns out that these 2 lines, or my function that is using these 2 lines, this is where you are setting the chip internal address, where to read from or to write to, and then you are using this function that is first selecting which chip on I2C bus is reading, and then how many bytes of it. It's a bit funky, this function here. It's a bit, not that intuitive. You should do it inverse. You should declare first which chip you are using on the I2C bus separately, and here internally you are requesting at which address, internal address of the chip, and then how many bytes you are requesting from that address. You can ask for more bytes, like 5 or 10, or the entire full chip to read from only this line, starting at a certain address, and it will increment itself, I believe, automatically when it's reaching the end. So when it's reaching the end of the address, is jumping to the next address and is reading it, and then it's jumping automatically. But I believe you have to use a loop for that, a for loop, for more bytes to read instead of 1. But this, like I said, this is a test program, so we are using the minimum. But I was curious about all these little details. So this is the entire setup you must have for this chip. These green wires are serial data and serial clock from Arduino to the chip pins. These 3 links, top 3 links, 1, 2, 3, are the address that are linked to the negative rail there. The 4th one is 0 volts linked to power the chip. That's the yellow one is the positive, and this must be linked to 0, which is write protect, and you must link to 0 if you want to write to the chip, to have the option to write to it. If you don't want to write and only to read from it, I believe it must be set to positive. And pretty much that's it. And also here is ground, 5 volts. You can see it inversed. It's that simple. And let me make a demonstration actually. Let me actually run the program. Let's upload it to my chip. There's nothing to see there because no LEDs are blinking or anything. We are writing to the chip with this program, and we are expecting, okay, and now I expect the 042. What this program is doing is writing this data into address 2, or this specifically a very long binary number 42 as an example. So this is the block of code for writing. You can see it here in the comment. Writing example, write 0x42 data to address number 2. And this is read example. This entire block of code is reading the data from that address 02. And here is actually showing it on the serial monitor as read 0x42. Yeah, you see? And that's all this code is doing. It doesn't show you blinking LEDs, but it is actually reading and is doing its job completely perfectly, and I'm very happy and pleased with this development. Another question I asked ChatGPT was, how is more correct to write 0x02 or 0x2 or 0x0002? Because it's 2 bytes here. That's why it's 4 numbers that you have to keep an eye for. Theoretically, from what I know, it doesn't matter which form you're writing it, but I was curious what ChatGPT will tell me about it, and I was a little bit surprised, as maybe you will be as well. All 3 are functionally equivalent, so it's the same thing pretty much, is showing decimal 2. So this is minimal hexadecimal. This is the way everybody is writing it, this way. Shortest and simplest, like I said, everybody is using it, including me, but I'm not really using hexadecimal that often, to be sincere. I didn't have the need for it. in what I did in my past projects. I did use it, but not as heavy. I'm not an expert. I'm not using it daily, is what I'm saying. I'm using it rarely, very rarely, when I need it. Works just fine, often used in simple code. This was interesting explanation. Great when precision matters. So makes it very obvious you are working with a 16-bit or 2 bytes address. Very interesting point, and I didn't think of it, but I've seen ChatGPT was using this format of showing 4 numbers in this hex, and I was wondering why it's not using only 0x1 or 0x2. Ideal for memory addresses, EEPROM offsets, or hardware registers. You want to emphasize that it's full 16-bit address. This is very interesting detail. I wasn't completely aware, and I wasn't completely accustomed with it, to be sincere. I'm a cheap person. I like to use the simpler, the smaller way of coding possible. But this is having some interesting logic inside that I was not particularly aware of it. After I managed to program, after I made this illustration page for this particular model that I'm having, after I figured out everything, after I understood everything, like I already explained, all this process of figuring this thing out, I took my time, I walk it slowly. And after a couple of days, after figuring all this out, after understanding how to address this chip, how to work with it, I was quite pleased with it. But I was having this feeling, this question in my head, what the hell should I use it for? In what practical project can I use it now that I can use it? Now that I can actually make a code for it, make use of it, that I can put it in practice? Where should I practically use it? And I asked this question on ChatGPT. So, okay, then why use serial or parallel EEPROM chips and not a single microcontroller with internal EEPROM, like for example AT24C32? Why external EEPROM chip? And don't tell me it's because the MCU is not having enough memory inside, because it does have sufficient enough not to use it fully in most of practical cases. Many MCUs like the AT24C32 already include internal EEPROM, which is often enough for small projects. So why would anyone still use external EEPROM chips? Let's dive deeper beyond the not enough memory argument. Preserve internal EEPROM lifespan. Microcontroller internal EEPROM often has limited write endurance, typically 100,000 cycles of writings, not readings, but writings. That's the most important thing. Like a flash memory, the flash stick that you are using all the time, on the same address, if you are writing 100,000 times, that address will weaken or get damaged or not work anymore. You cannot read anything from that damage after 100,000 writings. The chip will not go bad completely, but some of its addresses will not be accessible. Actually, they will be accessible, but you cannot read anything from it, or you can read only the same value that is stuck in that address and you cannot change it anymore. So either two of these versions you will have. So that chip, some of its addresses will get damaged. This is what I know, and this is how I know it. This is very, very interesting reason why you should use an external EEPROM compared with the internal EEPROM of the microcontroller. In scenarios like data logging every second. So this is very interesting. I didn't thought of it. I mean, I know about this detail. You don't use these chips like this IE is telling. I never actually thought of it, that you will want every second to do it, because I know this writing problem, and I'm not actually considering doing it like he is telling here. I don't think I will have a project that will use every second or every 5 seconds or even 10 to 10 seconds writing on an address or multiple addresses some data. So in scenarios like data logging every second, that lifetime gets exhausted very fast in a couple of months or weeks, depends. Using an external EEPROM offloads frequent writes, protecting the internal EEPROM of the microcontroller for more critical tasks like configuration storage. An example, a weather station that stores sensor data every 5 seconds to EEPROM, internal EEPROM will die in weeks. External EEPROMs can be chosen with higher endurance or replaced easily. This is very, very interesting detail as well. I also never thought on replacing EEPROMs. I swear to God, I never thought of it. So this little detail here is telling me that people in this world, crazy people, they are actually using, I don't know, tens, hundreds, thousands of EEPROMs for this kind of engagement, for logging every second, and they are changing the chip. They have hundreds of these EEPROMs with the same program in them, or just for data, blanked like that, and they are inserting them and changing those chips weekly, one per week, like that. That's crazy. That is crazy. But very interesting way of thinking, and very interesting use of the EEPROM chip. Very, very, very interesting. I know I will not do it myself, me personally, because I know the limitations. I want to keep the internal structure of the chip as good as possible, as long as possible. This is my instinct. This is what the good sense in me is telling me to do, to preserve and to take care of the device, not to push it to the limits, like second by second writing on it and erasing and writing again. No, this is crazy, quite crazy, but it appears some people are actually doing it. That's why I think it's very interesting. This is another very interesting argument, the separation of concerns, modularity. This is what I like, actually. I like modules. Electronics, for me, I like it because of its modularity. You can take little circuits, small circuits, and create a bigger and more complicated circuit. Somebody else, when he's looking at it from exterior, he doesn't know the little circuits inside it. He will see a very, very complicated electronic board or circuit, while you, the builder, you are seeing those modules that you use inside your big board, and you know that is that little thing that is doing specific function, and that is the other, and that's the modularity that I really like. And let's see what this guy is saying. Keeping configuration or calibration data in a removable EEPROM module allows swapping out MCUs without reprogramming, like this line here, replaced easily. Like I said, like hundreds of them, you can swapping them without reprogramming the microcontroller. Very interesting, because you are only storing data and the microprocessor is reading the data stored in your EEPROM. And from what I talked with ChatGPT, it told me that EEPROM can collect data directly from the sensor on the same I2C bus. Another very interesting point of using. So pretty much if you have a temperature sensor on I2C bus, you link it with the EEPROM, and I'm not completely sure how you link those two and how you send and write from the sensor directly into EEPROM. But my best guess is the microcontroller is doing it in the background. The microcontroller is taking the data from the sensor, is writing it into the EEPROM, and that's it. That's the only function that is doing, and from 5 to 5 seconds, that's all it's doing. And at the end of the month or the week, after 7 days, or better said, when it's detecting that the chip is full of data, then it's dumping all the data into a file, into a computer, not into a file, because a microcontroller doesn't know about files, but it can blip you on your mobile phone or on your computer, and you access a special program maybe that is reading or automated to read the entire chip of data and then erase everything to 0 or FFF and start again the same cycle, probably. I'm not sure, but it's a very interesting ensemble how to do things. Yeah, I'm not used to this thing. This is the first time when I'm delving into this kind of problems. Then keeping critical user data persistent even if firmware changes. So this is more for a factory or for a shop. There are shops with stuff in them, and I don't know. Example, in industrial equipment, if the main controller is replaced or upgraded, the EEPROM with factory calibration data is preserved. Very interesting, but I will never do it like this, most probably, me personally. Pre-programming in production. This is way beyond my user needs. EEPROMs can be pre-loaded during manufacturing with serial numbers, MAC addresses, or licenses before soldering the MCU. This helps in assembly line automation and simplifies provisioning. This is factory stuff that I don't feel I will have a need for this, most probably. For example, USB devices or Wi-Fi modules store unique IDs or certificates in EEPROM separate from firmware. Well, this is beyond my years. Firmware simplicity, portability. Also over my years, not really need this kind of functionality in my projects. Some platforms or bootloaders treat EEPROM as external configuration memory. You can use the same firmware binary across devices and only change EEPROM contents to tweak behavior, region settings, device role, calibration. Yeah, way over my years. No, I will not use it like that. I2C or SPI bus sharing. This is very interesting. Like I mentioned it already. External EEPROMs use standard interface like I2C or SPI, which are already used by sensor, RTC, and displays. You can just piggyback EEPROM on the same bus with minimal extra cost, just one chip. Example, my chip AT24C32 or 256 can be dropped into existing I2C lines or SPI lines with just a unique address or chip select pin. It's interesting. I have to actually make it to feel and to grasp its functionality. You learn it when you make it, pretty much. This is how I'm learning the best way, by making stuff. Other people, maybe they are way more smarter than me. They only read, they have that capability of retaining, sediment that knowledge into their memory, but it's not the same for me. For me, the experience is telling me a story that I'm not forgetting it very easily, even if I want to. That's why I'm experimenting. That's why I'm doing all my tests. Data portability. Some EEPROMs are socketed or deep packaged for easy removal. They are made specifically as a deep package to remove them easily, not as SMD package that are not that easy to remove. Technicians can extract and analyze EEPROM contents without touching the MCU. This is very interesting, very interesting. I'm still not sold out. I'm still in balance if I will ever do it like this, but this is a very good argument. I like it, the portability. Examples, arcade machines or factory machines store high scores or calibration in removable EEPROMs. Very interesting detail. All these arguments that ChatGPT is telling me about, I never thought of them. This, again, I'm repeating for the nth time. This is the first time for me to deal practically with the memory. I don't really need for an EEPROM. I was just curious how to work with it, to be accustomed to it, not to be alien from it. I want to know how to work with this EEPROM because from all my readings, from all my knowledge, I've heard and I've read that people are actually using EEPROMs in their circuits in special occasions. And that's why I was attracted towards this type of chip. Also, if I remember right, inside the motherboard from a PC, there is also EEPROM for storing all the BIOS settings. And that BIOS, you can replace it if the chip is burned or you have a corrupted BIOS chip or it's just fucked up from the factory, who knows, you can buy that chip with the BIOS inside it and replace it. I know this thing happened to a guy I don't remember who, if I watched it on YouTube or it was in real life, but I remember this detail that he actually replaced the BIOS chip. He buy it on eBay and he replaced it, and the motherboard worked after this little replacement. So I know this little detail about it. Very interesting, again, but very, I don't know, alien for my daily needs. I don't think I will make a project with this kind of functionality. It's nice to read about them, but in reality, I'm not completely sure what I will use such a chip for, practically, you know. Security, of yeah, I don't really care about security. This is bullshit. Yeah, no, well, bullshit for me at least. For others is very important, but for me, I don't really care. Nobody cares. All right, the next question. A good point about MCU internal EEPROM often has limited write endurance, 100,000 cycles, where data logging every second, data lifetime gets exhausted fast. But what if I'm not logging at all? Not every second, not every year. What if I'm just storing some predefined settings that are always used and depend upon, and that's it? Practically, it will be a reading EEPROM and not a write-read one. In this scenario, why use serial parallel EEPROM chip and not a single microcontroller with internal EEPROM, like, for example, ATMEL 328? Excellent and very fair follow-up question. You're absolutely right. If you're only storing predefined settings once and just reading them regularly, then the argument of write endurance doesn't apply anymore. So why use an external EEPROM in this case? Honestly, you probably don't need one. So what this line is telling me that EEPROMs are actually used for writing on them more than reading on them. It doesn't make too much sense to me, but this is what is implying, this is what is telling me. They are chips, these chips are made for writing on them, for continuous writing, or for multiple, and by multiple I mean thousands and millions of writings on them. Something in that range, many times. They are used for pretty much for writing data in them, and after a while reading everything, analyzing, and dumping all the writing and starting again, or something like that. It's what I'm thinking, you know. If the internal EEPROM in a chip like ATmega 328 is sufficient in size, then there's no good reason to add an external EEPROM. Very fair argument. I like it so far. Yeah, I give you a 10 from 10, ChatGPT, for this explanation is very good. But he is coming with a counter-argument here. Why an external EEPROM might still be used anyway. Even with your read-only pattern, there are a few corner cases where external EEPROM might still be used. Very interesting details here. MCU code is locked, flash only. It means the code in the microprocessor, in the microcontroller, is locked. You cannot access the code in it, and you can only access the data, pretty much. And the data is in the EEPROM. In some systems, the microcontroller is locked down and can't be reflashed easily. EEPROM chips allow you to update settings externally without touching firmware. Yeah, it's interesting, but I will not do it myself in my projects. Most probably, I will not do it. Swappable configuration module. External EEPROMs acts as a personality module, a chip that can be inserted into different devices to tell them how to behave. Pretty much different programs. This is useful for field reconfiguration or modular devices. Security through separation. EEPROM holds secrets, serial keys that are physically harder to extract from a separate chip than from MCU flash. Yeah, nah, not applicable to me. Conclusion, that's it. Really, that's it. This was a work hand by hand with the ChatGPT. I'm quite pleased that now I can have actual access to program this device, to actually talk with this device, to actually use this device, this little chip, while before I wasn't. So this is more advanced topic in electronics that no many people are interested in, no many people are using them. They don't feel the need to use these devices. This is high level, very niche topic. And I'm very pleased that now I can access and program these devices and actually use them in my future projects. I hope I will be able to use them. I watched a guy on YouTube, Diode Gone Wild. He's a guy from Czech Republic or something like that. He's having a website and he's having a lot of movies on YouTube. And in one of his movies recently, while I was doing all my research here on my EEPROM, I stumbled upon one of his projects. He worked on it many years ago, before 2000s probably. And he used an EEPROM for a clock to store settings, an external EEPROM. So this type of data, this type of knowledge is accessible to some people, but not really for everyone. Personally, I didn't know about these details, about all these nuances, what you can do until ChatGPT. ChatGPT really enhanced my knowledge about specifically serial EEPROM. I'm very amazed and pleased that I can actually be able, from now on, in the future, to actually use these chips. I'm very pleased about it. Yeah. And with this, I will end this very long movie. Thank you very much for watching, for listening on this very interesting and quite hard subject, and learn from my mistakes, learn from my achievements along with me. And also don't forget to leave a like, and I hope it will help you somehow have a better understanding about these memory chips that are out there, but not really as much used as they should be, in my opinion. and they can be used in some very clever projects that I don't think about yet, but I will push my brain, and also ChatGPT. I will make use of it as much as I can to find a suitable and practical for me project to actually use these chips more frequent in the future projects, not right now. Okay, thank you very, very much for watching, for listening, for understanding everything I said until here. I hope it will help you in any way. And with this, I say to you goodbye from your favorite artist electronist, Mr. Q12. Bye bye.